So I just want to start by just showing what my computer game is about. And it's more or less about this bottle of water here and being able to move it quickly from here to here. And that's the scientific challenge that we want to solve, not with water, but with atoms, picking up atoms and being able to move them quickly without having sloshing in the end. So we really aim at making the players understand the physics that is behind, because we hope that in understanding the physics they will become better players and they will generate better results for us. So, okay, so when you do this gamification, there's always a strategy, which is you take a physics concept, in our case the quantum computer, you take some of the elements from the computer games, you take something from the community effort, and then you get your game. And our game is the quantum computer game, and we're working on this in the context of a center for community-driven research. Okay, so before I bore you a little bit with the background, I just want to show you a little bit about the game. So here's a little bit about the game mechanics. I told you it's all about taking something in a container, moving it as quickly as possible from one location to another location. Now this here blue thing, it's blue because it looks like water, and this is in reality an atom, and it's the wave function, and we continually solve the time-dependent Schrödinger equation as the player is allowed to then deform the potential landscape. So you all know that computers have been developing really quickly over the past 50 years, from something that none of us were alive to see, and then to something that is really small. And that's something that has been accompanied by or driven by the exponential decrease in the size of transistors that you probably know as the Moore's law. So this has been a great benefit in many years, but at some point the downside of that is that we enter this quantum regime. So that means that quantum effects will start to be important at the size of single transistors. And that's actually already a problem now, because when we have the wires, then electrons are actually already starting to tunnel, quantum mechanically tunnel from one wire to another. So the chip designers are working on different things to do it, and another way is just to jump to another paradigm of computing, and that would be quantum computing. So in order to illustrate what quantum computing is, and now this is where I apologize to physicists, because I try to illustrate a little bit about the power of quantum computation. So we all have two hands, and that would be like the bits, the zeros and the ones. And if we take one person, then we have two different possibilities of one show of hands, right? And if we take, every time we take one more, then we have two more possibilities, right? And so you all understand probably that this is then the exponential growth that we get 2 to the nth different possibilities of shows of hands. And what I still find a little bit hard to understand is that if we were 300 people in this room and we were all allowed to raise one hand, then there would be more possibilities for us to raise hands than there are atoms in the whole universe. And I think that's the power to the quantum computer that is really fantastic. And how can we take advantage of that in a quantum computer? Well, a classical computer for me is just a black box. There are some zeros and ones that come in, and then there's a function calculated on these zeros and ones based on the. In quantum mechanics, the only quantum mechanics that I'll be talking about today is also the cat that people may know. So the quantum system that we have can exist in two states, in different states at once, which means if we have a two-level system, like the qubit, then it can be in both the 0 and the 1 at the same time. And now, again, for you and for me, maybe, right now the quantum computer can just be a black box, but now the input are these qubits, which means that if we have 4, then we have 16 different states that we can represent at the same time, and the black box calculates for us 16 different outputs. If we had 300 of those, we would be calculating more values in a single step than there are atoms in the whole universe. And that's the power of the quantum computer. So people who know quantum computers know that the story is not quite that simple. There are caveats, but the basic is that you really can do tasks that no computers in the world can do combined. And one of these tasks is prime number factoring, and that means that you'll be able to break much of the internet security if you had a large-scale quantum computer today. That's why lots of money is being fed into research here. And it's also difficult. So I just want to give you just a brief state of the art on quantum computers. They have been in existence for more than a decade now. And the first one was based on organic molecules, and they had 7 of these qubits, and they did the calculation 3 times 5 is equal to 15. So that's the prime number factoring that you see here, and if you could scale that up, that would be very interesting. Right now, it's not that impressive. And then for the last 10 years, people have been really working on it in different labs to try to implement in different systems here. Quantum computation has been implemented in different systems, but this record today is still only 14 qubits. And 2 to the 14th is still not a very large number. Okay, so we need to expand that to hundreds or thousands of qubits. But unlike regular computers, we don't need to expand it to billions of qubits. So that's where the hope is, that if we can just expand this here by a couple of orders of magnitude, then we'll have a really fantastic computer. The reason that they haven't succeeded yet, and I've also tried to build one of these, and it's really difficult. So there are lots of technical challenges, and that's where the idea for the quantum computer game comes. Try to help solve some of these fairly basic optimizational challenges, but they're just unsolved challenges on the way. And in order to see what do you need to do in order to build a quantum computer, you need to do 3 things. First of all, you need to have these hundreds or thousands of qubits. You need the ability to flip individual qubits, so 0 to 1 or anything in between. And that's where Sabrina's block sphere comes into the picture, because you need to be able to make any state between a 0 and a 1, not only zeros and ones at the same time. And then you need to do something that is called a 2-qubit operation. And for all the computer scientists, you know that there are NAND gates and NOR gates that are universal in making the software on this computer here. And in exactly the same way, if you can implement one of these 2-qubit gates along with the single-bit gates, then it's universal for quantum computation, which means I take all of these 3 steps together, and then I can build any sort of quantum computation code, which means it's fantastic from an experimental point of view, because in order to claim that I have a quantum computer, I don't need to make a very complicated program. I just need to be able to do all of these 3 things, and then I can say that it's an engineering task to do it well. Okay? And it's the proof of principle that I'm concerned about right now. So in my postdoc in Germany, I worked a little bit on setting up an experiment that had an artificial egg tray-like potential for atoms, where we could put individual atoms into each of these egg tray wells. So that's the picture here where we show that we could really put in individual single atoms into the wells, and we produced the coldest crystal in the world, fairly cold. And then a little bit later, we managed then to shine in an optical tweezer of light, so a laser beam which was focused on a single site and showed that we could flip qubits from 0 to 1 or anything between. And you can see here some patterns that we were able to write then using this, you could say, quantum dot matrix printer. Okay, so that means that in our experimental work, we've solved number 1. We have 300 atoms at our disposal. They're individual atoms. They're individually addressable. Very good. And now we only need to solve this second challenge of bringing 2 together and somehow making this 2-qubit gate, which we haven't done yet because it's really difficult. Okay, so that's the remaining operation. We didn't manage to do it, but we came up with at least a theoretical way to do it. So the theoretical way to do it was, I took my crystal, and then I blow away some lines here, and then I have transport lanes here. And then, in principle, I just need to be able to pick up this one atom here, transport it to here, and then over to here, and then we can make an interaction, we can make the gate. Okay? So the challenge here, now we come back to my water, because the atom should not be thought of as a ball. The atom is described by a wave function. Some of you know that. And the wave function is something that can behave very much like the water here. And that's why the challenge is very analogous to just taking a glass of water and moving it and avoiding these sloshing. Technically, sloshing means a mixture of higher excited states, and higher excited states means errors in the computation. Okay, so now we're ready to again see the scientific, or at least one of the scientific challenges. So here we have the atom. It's being transported. You may notice here a small indentation. That was the well that the atom was in the beginning, and then there was another indentation here for another well, and we wanted to move it from one well to another well while preserving this Gaussian shape here, which is the ground state of the atom and the potential. Okay, so that illustrates one part of the game mechanics. And now, if you think this looks nerdy and uninteresting, it gets even worse now, because we also want to give them possibilities of abstractly controlling now. So you saw that what you could control in the game before here was the position of this tweezer here and the depth of this tweezer here. So a 2-dimensional space. Okay, so I, as a physicist, I wouldn't play that game a lot. I would play this game here, where you see the intensity as a function of time, and you see the amplitude as a function of time. And now I want to manipulate this here, and then get the score updated live, right? And that's what this sort of cockpit type panel will do for you, where you can globally manipulate now the total path, and you always live see an update then of your score here. Let me just show you one of the most difficult games that we have, and that's the merging of two atoms. So now we have one atom here, we have an atom over here, and the idea is dump them into the same well, such that now technically one of them is in the ground state, the other one is in the first excited state. Okay, so that means that I should dump them in there, and in the end they should not be moving. So I take that, I'm already moving, and now I'm supposed to dump them in there, and they're supposed to be absolutely still. And I press here, and I'm supposed to get 100%. So that's a really difficult challenge.